This is a lecture in a series of lectures covering an introductory look at MOSFETs and their use both as switches and as controlled current sources for implementing analog amplifiers. And in this lecture, what we want to look at here is a fully AC coupled amplifier. So in a previous lecture, we'd introduced some improvements to biasing the amplifier, and we used a series of two resistors connected to the gate and an AC coupling capacitor between the input signal source and the gate to AC couple the input. But now we want to look at doing this both for the input and the output, and we'll work a little example to help make the concept more concrete. So here is our amplifier. Both of these are going to be tied up to VDD. We have RD, so R1, R2, and then we have C1, and I'm going to put infinity, meaning it's just very, very large. We're going to go to VI here. That's our input signal. And then on the output, we're going to AC couple our output as well. So this is a new part. We haven't looked at this before. We'll put a big capacitor here, and then we're going to put a load. Okay, and we'll call this VO, and this will be VI. So first, the way that we analyze this circuit. So let me say, what do we want to find? We want to find VO over VI. What is the small signal gain? Okay, the small signal gain. So we treat this circuit, or this amplifier, as in one of two regions. Okay, first one is the DC region, or DC mode. The other one is AC. So in the DC mode, we have no VI. VI is equal to 0. And what we're left with is just the biasing circuitry. Oops, no. And there's an open circuit. The caps are open. I should say that caps open. So that means the amplifier does not see the load resistance because C2 is open under DC conditions, and the gate does not see VI because the C1 capacitance is open. So here we have VGS, big VGS here, is equal to R2 over R1 plus R2 VDD. And we could write that IDS, the current flowing here, is equal to K over 2, big VGS, minus V threshold, quantity squared. And we could determine that the small signal gain, or the transconductance of the amplifier, is the square root of 2 K IDS. Okay, and that IDS being the IDS that we would calculate here from our VGS, and the VGS is going to come from our R1 and R2 and VDD. We could also solve for VGS in terms of IDS, and to do that we'd use this equation here. We can write VGS as being equal to V threshold plus the square root of 2 IDS over 2. Okay, and okay, we'll leave that for now. The AC circuit will look like this. We'll have our amplifier, actually, well, and I'll leave everything in here first, and then we'll do the small signal afterwards. So when I say AC here, I say when you're putting in this AC signal, then you're going to be shorted. VI will be shorted to the gate, so the capacitor is a short, and the output RL is connected through a short as well. Okay, and if we're doing the small signal analysis, what we have is we can turn off all the DC sources. So we'll do the small signal analysis there, where we'll turn off our VDD, and then our current source, our transistor gets replaced by a current source, which will be GM times little VGS. And then we have connected here a resistor, RL. Alright. And back on the input side, we just have little VI. And of course, it's going to two resistors. This would be R1 in parallel with R2, because VDD is turned to 0, so R1 here is effectively grounded. And we can write the small signal gain, VO, which is this voltage here, divided by VI, very simply as we have GM times VGS, but now VGS is actually VI. So GM little VI times the net resistance at the output node here, between the output node and ground. And what we have is RD in parallel with RL. Okay? So let's work a problem here as an example. Suppose VDD was 30 volts. The drain resistance was 5,000 ohms. Our current, our bias current, I'm going to pick to be 3 milliamps, and the reason for that is that VDD minus 5 kilo ohms times 3 milliamps, VDD is 30 volts, is going to be equal to 15 volts. Okay, so I'm going to bias my drain voltage out at halfway between ground and rail. So we'll say ID is equal to 3 milliamps. Let's say that the MOSFET has a K of 0.15 amps per volt squared and a threshold voltage of 2 volts. All right, and the question is, find R1 and R2 to properly bias the amp and determine the small signal gain. Little VO divided by little VI when the amp is loaded with a 1 kilo ohm or a 10 kilo ohm load. Okay. So what we need to do is we need to find VGS that corresponds, biasing VGS that corresponds to our bias current of ID, IDS of 3 milliamps. So I'm going to use this expression up here. VGS is equal to the threshold voltage, which is 2 volts, plus the square root of 2 times 3 milliamps divided by 2. Wait a minute, that's supposed to be divided by K, divided by K. Sorry, divided by K. And K is 0.15 amps per volt squared. Okay, that turns out to be 2 volts plus 0.2 volts. Okay, 2.2 volts. So What we need is, given 30 volts applied to R1 and R2, we want 2.2 volts here. This is R1, this is R2. So we have VGS of 2.2 volts divided by VDD of 30 volts is equal to R2 over R2 plus R1. Oops, R1. So this is number 2 up here. Now I could rewrite that and say that R2 is equal to R1 plus R2 times 2.2 over 30. Now, it turns out that all that matters for setting the proper VGS voltage is the ratio of R2 and R1. So let's add one other requirement. Let R1 plus R2 equal 100K. Okay. So if that's the case, then what we have is R2 would be equal to 100K times 2.2 over 30, and that is approximately 7.3 kiloohms. And therefore R1 is going to be equal to 100 kiloohms minus 7.3 kiloohms, or approximately 92.7. Okay, so we have found the resistors R1 and R2 for properly biasing the amplifier. Now we need to find the small signal gain. So find GM at IDS equal to 3 milliamps. GM is equal to the square root of 2 times K times IDS. So that's square root of 2 times 0.15 times 0.03. And that evaluates to 30 milliamps per volt. Sorry, this is a mistake. It's 0.003, 3 milliamps, right? That gives 30 milliamps per volt. Okay, so now find, let's see, 3, that was this guy right here. And then 4, find the small signal gain VO over VI. And we found that right here with number 4 as being the parallel combination of RD with RL. So that is 5 kiloohms in parallel with 10 kiloohms. And it's a minus sign, RD in parallel with RL times GM times, okay, that's it, times GM. So it's 5K in parallel with 10K times 30 milliamps per volt. And that gives us 3.3 kiloohms times 30 milliamps per volt, which, minus sign, which equals minus 100 volts per volt. And the way, let's draw some signals so you can see the way that the signals propagate through here. So let's say that we had, say, a VI here, and I'm going to actually put an offset on this VI just because I can. Okay, so this right here is going to be a capital VI, and this VI here will be actually equal to big VI plus, let's say, 1 millivolt or 10 millivolts times sine omega t. Okay. Now what will happen is when we apply this signal through the input resistor C, or input capacitor C1, we will have a voltage at the gate, VGS, that will have a bias point that is not related to VI, big VI. It will be related to just R2 over R1 plus R2 times VDD, and this will be equal to the 2.2 volts. This VI may be, let's say it was equal to 1 volt, or it could be minus 20 volts. And then the small signal that will ride on top of it right here, this signal will now be equal to VI equal to big VGS plus the same 10 millivolts sine omega naught t. So the capacitor blocks the DC, but it allows the AC to go through completely. So all of the AC portion of VI arrives at the gate. None of the DC portion arrives at the gate. The only DC portion at the gate is whatever is established by R1 and R2. And then we could, see if I can fit this on here. At the output, if we drew this as being VDD here, and I'm going to plot VO now. If we bias this halfway, the output voltage is going to be 100 times 10 millivolts, okay, so 1 volt amplitude, and it will, poorly drawn, it'll look like this. Okay, so this would be equal to, this is VDS, sorry, not VO yet, this is VDS, the voltage at the drain, will be equal to big VDS, which we solved to be 5 or 1/2 of VDD, or 20 volts, or, I'm sorry, 15 volts, right, plus what we have is our minus 100 volts per volt times our 10 millivolts sine omega t. Okay, and then lastly, what we have for VO is VO applied to our load resistance, okay, will be exactly the same signal, but the DC will be removed from it. So VO is this signal right here. And VO will be equal to 0 plus minus 100 volts per volt times 10 millivolts sine omega naught t. So from the output, outside I should say, if I apply some signal VI that has some peak-to-peak amplitude of 20 millivolts, what I'm going to get at the output is an output that is centered around 0, and the peak-to-peak value here is going to be equal to 100 times the 20 millivolts peak to peak, or 2 volts peak to peak. But it's going to be centered around 0. And no matter how much offset, this offset that we put in here at the input, call it V, big VI, it will not affect the biasing of the amplifier. And so the amplifier will always have a gain of minus 100 regardless of what the DC offset is at VI, because the input decoupling capacitor blocks the DC of VI from ever reaching the gate of the transistor. Similarly, the DC blocking capacitor C2 at the output prevents any of the offset at the drain from ever reaching the load resistance. And so regardless of where you were to bias the drain voltage, here we've done it at 1/2 of VDD, regardless of where that is, the bias point for VO is always 0 because of the coupling capacitor, or DC decoupling capacitor C2 at the output.